Hi everyone. So welcome back to 180 astrophysics questions. Today, again, I'm not actually going to do something on the list, but I'm going to do something just very broad that I have kind of been wanting to do for a while, just because otherwise I will forget how to do this. So today, actually, what I'm going to do is I'm going to derive a solution to the Kepler problem from scratch, starting from Newton's laws and the law of gravity, and we'll derive everything that we can. So let's go. So this will be kind of long, most likely. Okay, so the first thing is I'm not going to derive this first part, which is that I'm going to assume that you know that you can set up a two-body problem as center in a particular set of coordinates, which is if you normally have two masses m1 and m2. So that's m1 with some vector r1, and there's another mass 2 with some vector r2, then you can describe their entire motion as an RCM and a little r. And so RCM obviously is, since there's no external forces in this two-body system, it's just going to stay in the same place, and r is going to follow the normal equation of motion that we had before. So we're going to start with saying that F is equal to mu times r double dot, and this is equal to negative g m total mu over r squared. And so just to clarify, m total is the total mass, it's m1 plus m2. You can do this in doing the coordinate transform to center of mass coordinates. And mu is equal to m1, m2 over m1 plus m2, the reduced mass. Right. And so now what we're going to do is we're going to show, we're going to take two derivatives. Oh, sorry, I missed an r hat here. That's going to be very important. We're going to take two derivatives over here on the left side of r, which we can do by saying that r is equal to r times r hat. And so if you take the first derivative of this, r dot will be r dot r hat plus r hat dot. And r hat dot, you can do out all the Cartesian coordinates in general, but what I'm going to do is, if this is r hat and this is theta hat, then as time changes, it's going to move in this direction, in the theta hat direction. So r hat dot is going to be, so I'll write it over here. So r hat dot is going to be theta dot theta hat, and theta hat dot is going to be equal to negative theta dot r hat. And that's because it's moving in that direction. Okay, great. So this will become r dot r hat plus r theta dot theta hat. Now if you take two derivatives, then we do this again. So r dot dot r hat plus r dot r hat dot plus, so there's three things I have to do. So the first one plus the second one, which is r theta dot dot theta hat, plus the third one, which is r theta dot theta hat dot. And so gathering like terms, this becomes theta dot theta hat, and here's another one over here, so this becomes r dot dot r hat plus 2 r dot theta hat plus r dot dot theta hat. It's going to become minus, let me erase that smudge, minus, let's see, so this becomes minus r theta dot squared r hat. Right, okay, so now if you take this expression for r dot, so first of all we're going to cancel these mu's. If you take this expression for r double dot and you compare it to this side, you'll realize that the theta hat terms are going to collect, and so these theta hat terms are going to be equal to 0 because this is like plus 0 theta hat. So that means we have 0 is equal to 2 r dot theta dot plus r theta dot dot. And we're going to, let's see, so this is going to be roughly equal to d by dt of, I think it's going to be 1 over r d by dt of r squared theta dot. Yeah, so if you product rule this out, you're just going to get this. And as it turns out, this over here is proportional to the angular momentum L. L, as it turns out, is equal to, so it's r cross p, right? Which is equal to mu r cross v perpendicular. But then the magnitude of it is just going to be mu r times v perpendicular, which is just r theta dot. Right, so this is equal to, so this just means that 0 is equal to d by dt of L. So that's just conservation of angular momentum. This, we kind of assumed it by assuming that we were sticking in a plane. Well, we actually didn't even do that anywhere here. It's just because it's a central force, so it's, angular momentum is going to be conserved. And that's exactly what we showed over here. Okay, so now we take the r hat equation. This is going to be a little more effort. And so we collect the terms from this over here. We have r double dot minus r theta dot squared is equal to negative g, I'm going to drop the subscript t, over r squared. Right. And now what I'm going to do is I'm going to turn this into L. I'm going to eliminate the theta dot in favor of L. So we get r double dot is equal to, so the theta dot squared, so you multiply the top and bottom by r cubed, and then we get L squared over mu squared r cubed minus gm over r squared. Okay, and then you note that r dot r double dot dot is equal to 1/2 d by dt of r dot squared. So we'll multiply both sides by r dot, and then integrate with respect to t, right? And when we multiply by r dot and integrate with respect to t, on the left side, that'll give us 1/2 r dot squared, and on the right side, that'll be the same thing as integrating with respect to r, because it'll be integral of dr dt dt of stuff. Okay, so we're just going to do that. Without showing the work, this gives you 1/2 r dot squared is equal to L squared over mu squared. Integrate this with respect to r. So first we have an r to the minus 2, and then we have to add in an r, a negative sign, and a 2 over here. And we integrate this. This becomes a plus gm over r. And then plus a constant, which I'm going to call E. Yeah, I'm going to call that E, because it's going to be an energy. So I'll actually call it E over mu, just to emphasize that. So E is now actually an energy. So we move everything over and we multiply, and what we end up with is 1/2 mu r dot squared plus gm mu over r, and this m, remember, is m1 plus m2, so this is gm1 m2 actually, minus, sorry, I did that backwards, so this is going to be, let's do it in this order. I think that's this is going to be a little clearer. So I'm going to add this term first, L squared over 2 mu r squared minus gm mu over r, and that's going to be equal to E. And so you see here that all of this together is the kinetic energy, and this is all the kinetic energy in the radial direction to and from the center of mass, and this is all kind of the angular momentum kinetic energy. And this is just your gravitational potential energy. That's gm1 m2. This we're actually going to call V effective of r, And the reason for this is because then we can treat the radial motion separately, and it becomes very simple to analyze. And this is pretty cool, actually. So let me, this is actually my favorite part of the Kepler problem. Beyond that, it gets kind of crappy, and you actually have to like do integrals and stuff. So let's just do this. So what I'm going to plot here is I'm going to plot v effective of r. We have a part which goes as 1 over r down here. And then we have a part which goes as 1 over r squared, plus positive 1 over r squared. And if you add those together, it's going to end up something like this. So this is r, and this is v effective of r. And now this E here is going to actually be the energy of the orbit. So this is the kinetic energy plus the potential energy. It's equal to the total energy. And so if you have an energy that's bigger than 0 over here, then your orbit is going to actually be unbound. If you have it equal to 0, you're barely bound. If you have less than 0, you have this region over here where you will have ellipsoidal orbits. You'll just oscillate back and forth between two radii, a minimum radius and a maximum radius. And if you have the minimum energy possible, you actually end up in a circular orbit. So this v effective is a very useful way to think about problems, and especially in the radial direction.